Okay, kids, so we're back and we're looking at section 1.6 and we're looking at more involved equations of motion. Really, uh, when you're looking at equations of motion, there's really one equation for uniform motion. When the velocity is constant, the object's not speeding up, not slowing down, not changing direction. It's just this equation right here. When acceleration is zero, the equation you use is velocity average is equal to displacement over time. Done. Forget about it. But there's a danger here. Look, danger. Wrote it down here. There's a real danger here. And the real danger is using this equation, which is only for non-uniform motion, when we're doing questions that involve non-uniform motion. Never, ever, 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 ever use this equation right here, velocity average is displacement divided by time, when it is with non-uniform motion. The acceleration is not equal to zero. Velocity is not constant. The object is either speeding up or slowing down. Please keep that in mind. Now, we do already have an equation that involves non-uniform motion, involves acceleration not equal to zero. It's this equation right here. And we looked at it a while ago. I had you do some questions on it. We did some examples in the videos and things. And its acceleration is equal to final velocity minus initial velocity divided by how much time it took for that velocity change to occur. Now you can rearrange this equation, which I'm calling equation 1 here. I'm calling this equation 1. If you swap the position for time and acceleration, so basically what you're doing is you're multiplying each side by time and then dividing each side by acceleration, you can rewrite this equation like this. Time is equal to final velocity minus initial velocity, all divided by acceleration. It's the same equation, just algebraically rearranged. Then what you can do is you can multiply this equation that I'm calling 1a. You can multiply each side by acceleration. Well, if you multiply this side by acceleration, it cancels out. If you multiply this side by acceleration, you get acceleration multiplied by time. And that's what I have here. Acceleration multiplied by time is final velocity minus initial velocity. There you have it. Then what we do is we take this negative velocity initial and we bring it over to the other side, and we're left with velocity final is equal to velocity initial plus acceleration multiplied by time. This is yet another version of this equation right here, equation 1. This is version 1b. Similarly, we can take acceleration multiplied by time is equal to final velocity minus initial velocity, and we can take negative initial velocity, bring it to the other side, right? Bring it to the other side, and take acceleration multiplied by time and bring it from the left over to the right. So we're doing a double switcheroo here. We're taking negative initial velocity, bringing it from right to left. We're taking acceleration multiplied by time, bringing it from left to right to the other side, and you get yet another version of this equation 1. We're going to call this equation version 1c. So we do already have an equation that lets us analyze non-uniform motion. It was the one I introduced a while ago, and then it comes in all these different forms as well, just by rearranging the equation using some algebra. Now, if this was the only equation we had, it wouldn't be much to help us figure out physics problems. It would be very limited. So we need to make and build some new equations. They're like tools in a toolbox that allow us to solve more complex physics problems. So we're going to create another equation right now, and we're going to base it upon this graph right here. Now this graph right here is a velocity time graph. And in this velocity time graph, we have an object at time equals 0 moving at a velocity that I'm going to call VI, V initial. And then as time goes on, look what happens to the velocity. It's going faster and faster and faster and faster. And then this is the next point of interest. At this point, it's now moving with a new velocity called VF, velocity final. And how much time went by? Well, a certain amount of time which went by from here to here, that I'm going to call delta t. So it took delta t seconds for the object to accelerate from its initial velocity to its final velocity. Now, from this velocity time graph, we want to get position information. We want to get displacement information, right? Get displacement, get position. And the way to get that displacement or position information is to use the area under this function, the area under the graph. And we learned about that in the previous video lessons. So what I want is actually to find this area that I'm going to show you in yellow. There it is. So it's an irregular shape. I want to show you that. I want to find that area. So what I've actually done is said, look, it's an irregular shape. Let's divide it into two areas, the triangle at the top and the rectangle at the bottom. So that's what we're going to do. We are going to find the area here, area 1, which is a triangle, and area 2, which is a rectangle. So let's go about doing that. Now, this is the triangle. So I hope you remember that the area of a triangle is equal to the base times the height. The base times the height. Let's fix that up here for a second. I don't like what I see there. Let's get rid of that delta there. Area of a triangle is simply base times height. So there, that's gone. I didn't want that there. So area of a triangle is base times height, and then we take it and we divide it by 2. All right? Well, I'm going to use that right in here. Oops, let me get a color here. I'm going to use that equation right in here, base times height divided by 2, in coming up with an equation that will let me find displacement, because displacement is what you get when you get the area under the function. I'm going to find area number 1. I'm going to find the area of the triangle. Well, what is the base? The base goes from here. Let me get a color here for you here. The base goes from here to here, and it's along the time axis, x horizontal, which is time. So the base is delta t. What's the height? Well, the height is right here. The height is right there. Well, how do we get the height? Well, that's pretty easy. I know here is VF, and I know here is VI. So if I want to know the difference here, I just subtract. I know from 0 to here is VF, from 0 to here is VI, so if I subtract those two, I get what's left over. So I get a height of VF minus VI. So my height is VF minus VI, my base is delta 2, and then I got to divide it by 2, because that's the equation for a triangle. Now, hopefully this doesn't confuse you too much. I'll give you a real life example. Let's say this was 5 up here, velocity final was 5, and velocity initial was 3. Well, from here to the top is 5, from 0 to here is 3. Well, what's left over? 5 minus 3, or 2. That's all I've done here. Next, I want to find the area now of the rectangle here. Well, that's easy. The area of a rectangle is, right, the area of a rectangle is just length times width. Now I'm going to use that equation right in here for area 2. What is the length? Well, the length goes from here all the way to VI. What is the width? It goes from here to here, which we already know is delta t. So here is the area number 2, a rectangle. It's VI times delta t. So I have found the area under this irregular shape by dividing it into these two parts. And I have VF minus VI, all in brackets, multiplied by delta t over 2. That's area 1, the triangle. And I have VI times delta t, that's area 2, the rectangle. So now what I'm going to do is I'm going to do some distributive multiplication and distribute the time into the bracket. So I get VF times delta t, and then I got to divide it by 2. So I create this term here, VF delta t divided by 2. Now I'm going to take this delta t and I'm going to multiply it into the negative VI. What do I get? Negative VI times delta t, and I still have a 2 at the bottom. So this term here now gets made into 2 terms right there. This term turns into 2 terms. And the VI times delta t, that just continues. So this term right here, I just repeat. I just keep copying it down. So now, being the math students that we are, we're going to collect like terms. These two are like terms. Look, I have VI delta t, and here I have a negative VI delta t all over 2. So I have a positive whole and a negative half, which these two combine to give me VI delta t all over 2. The VF delta t all over 2 does not change, so I just bring it down here and I repeat it. And that leaves me with now a third equation. Now a third equation. Oops, that's an error right there. Let me fix that. Not the third equation. This is the second equation for non-uniform motion. So here is now another equation, a second one for non-uniform motion, and it is delta t is equal to VI delta t all over 2 plus VF delta t all over 2, except no one writes it like that. What they do is they factor out a half out of each term, so the half gets factored out front, and they factor out a time, and the time gets factored out back. So usually this equation is written like this. Delta D displacement is equal to a half of adding VI plus VF, close the bracket, multiplied by time. That is our second equation of motions. For non-uniform motion, acceleration does not equal 0. We now have 2 equations. That makes our ability to solve problems even easier. We're going to build even more equations. Okay, now it's the third one. I lost count there. So now we're going to make a third equation. How are we going to make a third equation? Well, we're going to take equation 1a, which is right here. Here's equation 1a. And we're going to substitute equation 1a into equation 2. Equation 2 is right here. We just made it. Delta D is equal to a half VI plus VF, all in a bracket multiplied by time. And we're going to plug in where the delta T is. We're going to plug in what delta T equals. VF minus VI all over acceleration. It's the vector. Make sure I put the vector in there. So how do I do that? Well, I repeat the delta D. I write that down again. The half comes down again. This bracket VI plus VF, it comes down again. But the delta T is replaced by this. So I put that in the place of delta T. What do we do now? Now we have to multiply. Now we have to multiply. Well, the denominator is easy to figure out. I got a 2 in the denominator here. I got an acceleration in the denominator here. So my denominator is just those 2 multiplied together. 2 times acceleration. The numerator, we need some work. We got a 1 here, so multiplying anything by 1 isn't going to do much. But now I've got 2 binomials that I want to multiply, so I have to use my old friend and yours, FOIL. First, outside, inside, last. First, outside, inside, last. So let's do that. The first term from here times the first term from here gives me VI times VF. There it is right there. VI times VF. Outside. VI times negative VI. That gives me negative VI squared. There it is. Negative VI squared right there. Negative VI squared. Inside. All right. Inside gives me VF times VF, which is positive VF squared. There it is right there. Positive VF squared. Last. Last is VF times VI. VF times VI. So that leaves me with, VF times negative VI. I forgot the negative sign there. VF times negative VI. So that leaves me with negative VI VF. I just multiplied the last terms. There you have it. Here's the next stage in the equation. The delta D equals this. Now we're going to collect some like terms. If you take a look at this, the VI, VF and the negative VI, VF, well, they're going to cancel out. It's like 1 minus 1, 0. They're gone. So the first term and the outside term, they subtract away. Gone. So we're left with negative VI squared plus VF squared in the numerator and 2 times the acceleration in the denominator. Now, usually this equation is written just like this. And now we have a third equation for non-uniform motion when acceleration does not equal 0. There it is. Displacement is equal to velocity final squared minus velocity initial squared all over 2 times acceleration. That is our third equation. And we've got more equations to make. Okay, we're going to make a fourth equation. How are we going to do that? Well, we're going to substitute equation 1b. Here's equation 1b. There it is. Vf is equal to Vi plus a delta t. Final velocity is equal to initial velocity plus the acceleration multiplied by the time. And we're going to substitute it into equation 2. Here's our old friend, equation 2, right there. This is the equation we made with the graph just a few moments ago. So, where the VF is, where this VF is, so where this VF is, you see the VF is right there? We're going to replace it with something that's equal to VF. We're going to replace final velocity with initial velocity plus the product of acceleration and time. And that's what I do. Look, I replace the VF with that. Now, within this bracket, I'm going to collect like terms. Look, I have a VI plus a VI gives me 2 VI. The half remains, the bracket remains, the acceleration multiplied by time remains. I close the bracket and I still have this delta t at the end here. I still have this, that's a delta t. I still have this delta t at the end. So the thing we got to be careful about here is I got a bracket here. I got a bracket here. Okay. And we're going to multiply into the bracket. Well, what are we multiplying into the bracket? Well, we're going to multiply a half into the bracket. And we're going to multiply the delta t into the bracket. We're going to do distributive multiplication. Well, let's do that. A half times 2 gives me 1, and I still have a VI here. So a half times 2 VI leaves me just with VI. Then a half times acceleration multiplied by time gives me a half acceleration multiplied by time. I just brought the half in. Now I'm going to bring the time in. So I'm going to multiply each of these terms. Right? I'm going to multiply this term by time, and I'm going to multiply that term by time. So I bring that in, and I get the fourth equation. Delta D is equal to VI, that is now multiplied by time, plus a half acceleration delta time multiplied by another delta time, which leaves me with a half a delta t squared. So the fourth equation is displacement is equal to the product of initial velocity and time plus the product of half acceleration multiplied by time squared. This is your fourth equation. Okay, the fifth and final equation we're going to create. We're going to substitute equation 1c. Here's equation 1c right here. Initial velocity is final velocity minus acceleration multiplied by time. There it is. And I'm going to substitute it into equation 2, our old friend that we created with the graph. So what are we going to do? Well, okay, you see where the VI is? I'm going to get rid of the VI and I'm going to replace it with what VI is equal. And that's what I've done here. Look, here's the VI, but I replaced it with what it's equal to. Then I'm going to collect like terms, like a VF here and a VF there. It gives me 2 VF. And I still have this minus acceleration multiplied by time. The half, which is on the front of the bracket, is still there. And the time, delta t, which is at the outside to the back end of the bracket, is also still there. What am I going to do now? Well, I'm going to multiply the half in. Distributive multiplication. A half times 2 VF gives me VF. A half times negative acceleration time gives me negative half acceleration time. And then I'm going to do distributed multiplication again, and I'm going to multiply in the time. So now displacement is equal to VF multiplied by time. I'm bringing the time in, minus a half A delta T squared because I multiplied that last part in. So now I have created the fifth and final equation for non-uniform motion. Acceleration is not equal to zero. So here we have it, these five wonderful equations. This one here is the defining equation for acceleration. It's the first one we saw. This equation here we got from the graph by finding the area under the curve, this one here. And then these other three we found by somehow combining these two in various ways. So it's these two being combined that led to this one, that led to this one. That's a horrible arrow. That led to that one. So we have these five equations. I strongly recommend that you put them on on your equation sheet, which you should have started already, so that all your equations are in one place. So I don't want you to worry about all that other stuff we did where we created these equations. Holy smokers, you're not responsible for that. What you are responsible for is knowing these equations and using them to solve more complex non-uniform motion kinematics problems. So these become tools. I'm never going to ask you to derive them or to recreate them like I just did. But I am going to ask you to be able to use them, and we're going to use them in the next video, which is a whole bunch of practicing going on for more complex kinematic equation problems, and we'll see you in the next video. Have a great day. Bye-bye.